there, only I am giving you the result. So what is the effect or what is the modification of Rutherford scattering if we include the spin half contribution? If we include the spin half for the projectile, what we get is Mott scattering cross section. Basically Mott scattering, and the cross section is basically Rutherford scattering along with this term. This is due to spin half contributions. Of course, theta is the angle of the scattering. Right. Next, দেখো এবারে আমি জাস্ট একবারই লিখছি the effect of recoil of target and the effect of interaction of the magnetic moment of target along with charge. The entire thing can be written like this over here. So this is the Mott scattering cross section, effect of recoil number 2, and number 3 the magnetic moment interaction. And this tau is basically this term. And what is this q square? Now you see the electron, they are interacting with the proton, right? So what we can have, initially we have elastic scattering, but we can have of course a transfer of momentum later on for high energies, right? And you see here I have shown you the value for the transferred momentum. You see? So you can think of what we are doing here. We started with the elastic scattering cross section of Rutherford. We did 3 modifications. We ended up with this. This is known as Rutherford formula. We ended up with this expression for elastic scattering. And now you see, since we already have the recoil of the target, right? Recoil of the proton basically, which has to be taken into account. So we cannot use the previously talked about 3 momentum. We have to use 4. We have to talk in terms of 4 momentum. And here I have shown you what is the transferred 4 momentum due to this interaction. Just initial minus final momentum square, and this can be approximated written like this. And here I have also introduced this new quantity capital Q square, which is just negative of small q square. Nothing else, nothing more has been done. And now if I write this expression for particularly the electron proton scattering, then we get this part of this sort of expression. So there are 3 terms again. First Mott scattering term, next your recoil proton term, and then your magnetic moment interaction term. So that's it. So from here this is what you can get the picture. So basically we did not derive it, but basically we discussed from Rutherford scattering to this Rutherford formula how we can achieve after doing these 3 modifications, and also we estimated the transferred momentum. This is what we have done. Okay, so we were just talking about the Rutherford formula, right? Now it is important to remember regarding that for a given energy of incident electron, there is only one independent variable theta, and you can also see this from this expression between E and E prime. Fine. Now we have incorporated till now in the Rutherford scattering cross section 3 effects: spin half of electron number 1, number 2 interaction of recoil of proton, and number 3 effect of the magnetic moment, right? What about the fact that proton also has a size, finite size of the proton? You see, for that, while doing experiments, this is what we observe. This is how, and for that we have done the parameterization. So this is the d sigma d omega. This is after Rutherford formula, where the effect of finite proton size has been taken into account. So this is your again Mott scattering cross section, This is the effect of recoil of proton. But this term here, you will see, compared to the previous case of just 1 plus q square into tan square theta by 2, we have included two very important factors, g square, gm square here. Now what are these? Basically, this g square and gm square, they tell you about the size of the proton. And when I say size, I mean they are basically, you can call them electric form factor and this one magnetic form factor. Now at low q square, this g square, this is basically the Fourier transform of electric charge of proton. And regarding the gm square, this is basically the Fourier transform of magnetic current density inside the proton. Right? Now let me go to the limit of q square tending to 0. That means the virtual exchange photon, its wavelength is very large. So basically electron sees the entire proton. In this case, G and Gm are both equal to 1. And you can see that this expression reverts back to your Rosenblatt formula. In this case. Now, experimentally, it has been observed that G and q square is equal to 0 is equal to 1. This is okay. But for Gm, experimentally it is observed that it is not so. It is basically equal to mu p. So, anomalous magnetic moment of proton. So, this in fact tells you about, gives you a hint about the substructure of the proton. Right. Now, even more experimental results at higher q square, they gave you this sort of expression for gm square. 2.79 divided by this term, q square dependent term. And from there, if you do a Fourier transform of it, you will get this proton charge density. This is experimental, remember. This is from experiments. And so this is the nature of the proton charge density. Rho 0 is a constant and A is around 0.24 Fermi-meter. And from this result, you can calculate this root mean square charge radius of proton to be around 0.8 Fermi-meter. Okay. So, this is what we have covered today. So, we have started with Rutherford scattering and included one by one the effect of 4 factors, right? And finally, we have concluded with the experimental observation of the proton charge density, right? And the calculated value of root mean square charge radius of proton.